Hey students, welcome. In this lecture from our elementary statistics course, we're going to be learning about part 1 of section 3.3, so measures of relative standing and box plots. Okay, so in this video, which is part 1, we're just going to be focusing on z-scores, and then we're going to get our feet wet with percentiles. Okay, so z-scores, and then an introduction to percentiles. So the slides from this section cover more than just z-scores and percentiles. So in part 2 of the video, we'll go ahead and move on and talk about percentiles and quartiles in more detail. Okay, and then we'll also learn about box plots in part 2 of this video. Okay, but we're going to start with z-scores, which is probably the most important concept in this section. So we're going to learn that first. So what are z-scores and why are they so important? Well, a z-score or standard score or standardized value is the number of standard deviations that a given value x is above or below the mean. The z-score is calculated by using one of the following formulas. Before we even look at these formulas, I do want to tell you something. They're technically the same formula. Okay, it's just the first formula is the formula for the z-score of a sample. The second formula is a formula for the z-score of a population. But they actually have the same placement of all the variables here. So if you'll notice, for the sample z-score formula, it's z equals x minus x bar all over s. For a population, it's actually the same exact formula. It's just instead of x bar and s, we have mu and sigma. But other than that, the formulas are identical. And the reason I say they're really the same formula is remember that x bar is the sample mean. Mu is the population mean. So all that's changing here is they're replacing x bar with mu, but they're both representing the mean of the data set. Same thing with the denominator. So here for the denominator, S is the standard deviation for the sample, and sigma is the standard deviation for the population. So because these are basically the same formula, you can use either one, but in most cases, we're going to be using the first formula because obviously in most cases, we're going to have a sample and not a census. So we won't know mu and sigma. So this is the one that we're going to be focusing on. All right. So this is the formula we're going to use to learn how to calculate a z-score. And a z-score is very useful because it indicates the number of standard deviations that a given value, data value x, is above or below the mean. So x represents an individual data value. Okay, so before we jump into an example, let's talk a little bit more about why z-scores are important, and then we'll go ahead and calculate some z-scores and learn how to compare them. Okay, so important properties of z-scores. A z-score is the number of standard deviations that a given value x is above or below the mean. Z-scores don't have units of measurement, which is nice because you can find a z-score for any set of data values, and then you can use it to compare that data value to a data value in a completely different set of data values, and it will tell you the relative importance of each. So in other words, how far above or below the mean you are. Okay. Another important property of the z-score is it lets us easily use the range rule of thumb, which we learned in the previous section. So the range rule of thumb is actually even easier when you have z-scores. So it turns out that a data value is significantly low if its z-score is less than or equal to -2, and a data value is significantly high if its z-score is greater than or equal to +2. So then we actually have a picture for this that I'm going to skip ahead to. So even though it doesn't say it in our book or on the slides, why z-scores are really useful is one reason they're really useful is because the range rule of thumb is very easily determined for each z-score. So this right here is the range rule of thumb, but it's stated for z-scores. So we did do this in a previous video, actually the section before 3.3 in 3.2. We learned about the range rule of thumb. But then the nice thing about z-scores is you can very quickly determine whether a value is not significant if your z-score is between -2 and +2 in this yellow portion, or if it's significantly low. If your z-score is smaller than -2, we automatically know that it's significantly low. And likewise, if your z-score is greater than or equal to +2, then the range rule of thumb says that that data value is a significantly high data value. And here are the inequalities that I was just mentioning. So significantly low values would be a z-score that's less than or equal to -2. Significantly high values would be a z-score that's greater than or equal to +2. And then values that are not significant would be z-scores between -2 and +2. Okay, so that yellow part in the middle. And the range rule of thumb is just one application of z-scores. Z-scores are actually used all the time, and we'll be coming back to them over and over again through the rest of our statistics course because they're so important. We'll be using them particularly in chapter 6, chapter 7, and chapter 8. But we will probably also see them in some of the earlier chapters from time to time. Okay, so the range rule of thumb already gives us a reason to learn about z-scores. Okay, so going back to important properties of a z-score, one more thing I wanted to talk about before we actually calculate a z-score is if an individual data value is less than the mean, its corresponding z-score is a negative number. Okay, so just going back to that picture, if you have a z-score of 0, that means that your data value is the mean. Okay, so the mean for a z-score would be a z-score of 0. So this is the mean right here. Z-score of 0. Okay, and then besides the range rule of thumb, they're very useful. Z-scores are very useful because, for example, if you have a z-score of 1, that would indicate that you are 1 standard deviation above the mean. And a z-score of -1 would be a data value that's one standard deviation below the mean. Okay, and then so obviously if you have a z-score that's a decimal, that also tells you how many standard deviations you are above or below the mean. So for example, if you have a z-score of negative 2.3, let's say we have a z-score of negative 2.30. That would indicate that we are that data value x is 2.30 standard deviations below the mean. Okay, so the minus tells you if you have a negative z-score, that's how many standard deviations you are below the mean, and a plus, a positive z-score, would tell you how many standard deviations you are above the mean. All right, so z equals negative 2.30 as an example indicates that our data value is 2.30 standard deviations. I'll just write an abbreviation here. 2.30 standard deviations below the mean. Okay. And then if you have a positive z-score, that will indicate the number of standard deviations your data value is above the mean. Okay. All right, so let's actually use the formula and calculate some z-scores. All right, so we're going to jump into an example now. And in this example, we're comparing the weight of a quarter and adult body temperature. Okay, so comparing the weight of a quarter and adult body temperature. So which of the following two data values is more extreme relative to the data set from which it came? That's an interesting question. So the first data value is a 99-degree Fahrenheit temperature of an adult. So, and this is from a data set where there were 106 adults in the study with a sample mean of, that's supposed to say x bar. Okay, sample mean x bar equals 98.20 degrees Fahrenheit, and sample standard deviation, S, equals 0.62 degrees Fahrenheit. Okay, this is the first data value, and that's representing the temperature of an adult human. Okay, the second data set is the weight of a quarter. So a 5.7790 gram weight of a quarter, that's among 40 quarters with sample mean, once again, that's supposed to say x bar. I'm not sure why it's displaying it on my recording studio as x, but that's, once again, the sample mean is supposed to be x bar for the formula. So x bar here is 5.63930 grams, and the sample standard deviation for quarters would be S equals 0.06194 grams. Okay, so in order to answer their question, what we need to do is we need to find the z-score for both the temperature of an adult and then also the weight of the quarter. Okay, so let's just start with finding the z-score for the temperature of an adult. Okay, so for the temperature of an adult, we said that we have a 99-degree Fahrenheit temperature, so that's actually the same as x. Okay, so your data value is the same as x. Okay, so here, x equals 99. That's in degrees Fahrenheit. And then for the sample mean for temperatures, x bar equals 98.20. Okay, so x bar equals 98.20. And then the last thing we need for the z-score formula is S equals 0.62. Okay, so S equals 0.62. Okay, and these data values are for, these statistics here, the data value is 99, and then we have the mean is 98.20, and the standard deviation is 0.62. These are for the temperature of an adult. So let's go ahead and use the z-score formula for these and see what it tells us. Okay, so these ones right here are for the temperature. Okay, so we go ahead and write down the formula. So the z-score formula, this is obviously going to be for a sample. That's why I use x bar and s. So it's going to be the sample z-score formula. So z equals x minus x bar all over s. Okay. And I've been told that my s's look like 5s, so I'm trying to work on that. But I apologize if they look a little wonky, but I'm trying to make my s's not look like 5s anymore. Okay, so anyway, what we've got here is all we really have to look at is the right side of the formula and plug everything in. So here x, we said, was 99. And then minus x bar, so that's going to be minus 98.20. I'll just write 98.2 because we don't want to really round until the end, but we don't need to write a 0 if it's the last digit. Okay, so 99 minus 98.2, that's x minus x bar. And then this is all over s, which is 0.62. Okay, so it's definitely recommended that you use a calculator on these problems. So here we've got our z-score for temperature. So just so you know, in your homework, they ask you to find the difference first, the difference between your data value x and your sample mean x bar. So just so you know, for your homework, when they ask you to find the difference, that's this right here. So what I'm circling in this different color here, that's known as the difference. And the reason it's called the difference is you may or may not remember, but difference in math means subtract. So 99 minus 98.2 is the difference here. Okay, so when you're doing your homework, the first thing they ask you to do is to find that difference, which, like I said, you want to do on a calculator. So 99 minus 98.2. Although that one's easy enough, we could do it in our head. So that's 0.8. So here the difference is going to be 0.8. Okay, so we have 0.8 over 0.62. And I think the reason on our homework for Pearson, I think the reason that they have you do the difference first is just to make sure that you're doing your order of operations correctly. Okay, so first you subtract on your calculator, that gives you the difference, which here is 0.8, and then you go ahead and divide. So we're going to go ahead and do 0.8 divided by 0.62 on our calculator. So that gives us 1.90. 1.90. Oops. I don't know why I wrote a 2 there. Okay. 1.9. Oh, I'm sorry. I misspoke. Okay. So the z-score that we got here is 1.290. Okay. 1.290. Now, when you are calculating z-scores, once you get to the last step here, you want to round to 2 decimal places. So let me actually go back to the slides really quickly just to see this page. So the round off rule for z-scores, which is what we just calculated, the z-score, round z-scores to 2 decimal places, such as 2.31. All right, so really all we have to do here is just count out 2 decimal places. And then here, the next digit is 4 or lower, so we round down. So our z-score for the body temperature is going to be z equals 1.29. All right, now what does this tell us? This z-score actually tells us that we are 1.29 standard deviations above the mean. So that data value, which was a 99-degree Fahrenheit body temperature, is 1.29 standard deviations above the mean. And the mean here was 98.20 degrees Fahrenheit. Okay? All right, so that is our first z-score. So I'm going to go ahead and erase all this while I go back to the slides. Okay, so all these problems are also worked out on the slides for your convenience. So we can see here, without writing out the second one again, because that took up a bit of video time, we're able to see that they got the same value. For the first one was 1.29, and then for the weight of a quarter, they used the same exact formula. So z equals x minus x bar all over s. And so then they went ahead and they plugged in the information for the quarter. So z equals x, which was 5.7790, minus x bar, which was 5.63930. Notice they're not rounding anything when they're plugging everything in here. You don't want to round until the last step. Okay. And then that's divided by S, which was 0.06194 grams. All right, so if you want to go ahead and make sure that you're able to plug things into your calculator okay, you can just use the example I just gave you, and then go ahead and do the weight of a quarter, which is done right here, and make sure you get 2.26 after you round it. But again, you don't want to round any of these numbers. You just want to round when you get to the final number, just like I did, okay? So anyway, we can see that we have these 2 z-scores. I don't know why this board is being so difficult to erase. Maybe it's because I wrote too much. But anyway, looking at these 2 z-scores, what do they represent? Well, we already said that the z-score of 1.29 means that we're 1.29 standard deviations above the mean. That's for the body temperature. And then this other z-score for the weight of a quarter, we got a z-score of 2.26, which represents 2.26 standard deviations above the mean for the weight of a quarter. So kind of a cool thing here is we're able to compare these two z-scores even though they're from completely different data sets, right? I mean, who knew that you could compare a data value for human body temperature to the weight of a quarter, and you're actually able to notice which one is more extreme. Well, which one is more extreme? When they ask us that question, well, which number is larger in magnitude? Well, 2.26 is more extreme because it's a bigger number, a larger number in magnitude. It's larger than 1.29. So we would say that the weight of the quarter is actually more extreme. Okay. So the book's interpretation is pretty similar to what I just said. So the z-scores show that the 99-degree Fahrenheit body temperature is 1.29 standard deviations above the mean, and the 5.7790 gram weight of the quarter is 2.26 standard deviations above the mean. Because the weight of the quarter is farther above the mean, it is the more extreme value. A weight of 5.7790 grams of a quarter is more extreme than a 99-degree Fahrenheit body temperature. Okay? So that is an interesting example. It's mostly interesting because it's something that you might have not known that you can do. And just for your homework, when they ask you which one is more extreme, if that shows up, if you have a negative number, just kind of ignore the negative for your z-score when you're answering the question, which one is more extreme. So for example, if you have a z-score of negative 3.12, that would be more extreme than a z-score of negative 1.23. So it's whichever number is further away from 0, if that makes sense. So you can basically just ignore the negative and look at which number is bigger in magnitude. Okay, cool. So we've already talked about the range rule of thumb. We can see that these z-scores that we just looked at, we can see where they are on the graph. So we had the weight of a quarter was 2.26, and then the body temperature was 1.29. So 2.26 would be right about here. So a z-score of 2.26 is actually considered significantly high. So that weight of the quarter would actually be considered a significantly high value. And if you want more information about the range rule of thumb, definitely watch my videos from the previous section, from section 3.2 of the same book. Okay? But the other z-score we got of 1.29 for the body temperature would not be significant because that's between 1 and 2. Okay? Cool. So let's do another word problem just to make sure that we're solid on z-scores. Okay, example, is an earthquake magnitude of 4.01 significantly high? This problem has a lot of text, but we just want to focus on a little bit of information here. This is way too much information, so we have to parse through it and focus on what's important. Okay, so among the earthquakes listed in data set 24 from our book, Earthquakes, one of the stronger earthquakes had a magnitude of 4.01. The magnitudes are measured on the Richter scale, and only earthquakes of magnitude 1.00 or higher are included. The 600 magnitudes in the data set have a mean of 2.572 and a standard deviation of 0.651. For this data set, is the magnitude of 4.01 significantly high? So, as you might have already guessed, what we're going to be doing here is calculating the z-score of this data value of 4.01. And like I said, most of this information we don't need. all we really need is the stuff for the z-score formula. So the z-score formula is z equals x minus x bar all over s. Okay. So we just need to identify x, x bar, and s, and then plug them in. And then we'll use the range rule of thumb to determine whether 4.01 is significantly high. Okay. So which one is x? Well, they're asking us about an earthquake of magnitude 4.01. So that's actually going to be the data value x. So that's what they're asking about. So x here is going to be the 4.01. And then remember that x bar is the mean. So here the mean is 2.572. So 2.572 is x bar. Okay. And then it's a little hard to read. Let me erase some of that. And then the standard deviation, remember that's s. So we also need that. So here they say the standard deviation is 0.651. Okay, so that is s. There's not really any room to write an s here. Teacher problems. Okay, so plugging everything in to this formula, we have x minus x bar all over s. So x is 4.01 minus x bar is 2.572 all over s, which is 0.651. Okay. And then once again, when you're doing your homework, when you're doing these z-score problems, they're going to ask you to find the difference first. So here the difference is just the numerator. So the difference would be the 4.01 minus 2.572. So to do your homework, you would just type this in, the numerator first in your calculator. So 4.01 minus 2.572. That gives us a difference of 1.438. Okay. And then we still have to divide. So we have 1.438 over 0.651. So we want to do that division on a calculator. So that should give you 2.208 for your z-score. Okay, and then so since our z-score is 2.208, we still have to round it. And remember, we're always supposed to round z-scores to 2 decimal places. So when you have something like this, 2.208, what you do when you're rounding it is you write out 3 digits, 3 decimal places. You look at 2 decimal places, which is the 0, and then you look at the next digit. Here, because it's 5 or higher, we round this up to z equals 2.21. Okay, so z equals 2.21 is our z-score. And then they also asked us whether this z-score is significantly high. And if you already remember what I said about the range rule of thumb today, the answer is yes. So let's go ahead and see why that is. Okay, so let me go back to the slides. So the magnitude of 4.01 gave us a z-score of 2.21, which I just showed you once again in great detail. And for the book's interpretation of that z-score, they say the magnitude of 4.01 converts to the z-score of 2.21, and because that z-score is greater than or equal to positive 2, the magnitude is significantly high. Okay, so let's go ahead and go back to The range rule of thumb, that's what we need to use here. I'm going to try a different rag for erasing this board because this board is not erasing very easily. So maybe it was just the rag that I chose. But anyway, our z-score was 2.21. And then if you just look at this picture here for the range rule of thumb, hopefully you can easily see that 2.21 is greater than or equal to 2, so it's significantly high. In other words, it would be somewhere here to the right of 2, and 2 is the cutoff for significantly high values for z-scores. Okay? So once you get comfortable calculating z-scores, it actually should be very quick to use the range rule of thumb, and it's also very easy to compare z-scores, as we did in the previous example. Okay, but the magnitude is significantly high because 2.21 is greater than or equal to positive 2. All right, so the other thing I wanted to talk about in this lecture, which is part 1 of a 2-part video, is I wanted to, as I said, get our feet wet with percentiles. So percentiles are measures of location, which is another way of saying it's a measure of relative standing. So when they say relative standing, what does that mean? Well, relative means how important something is compared to the rest. So the z-scores told us how many standard deviations we were above or below the mean. And then percentiles are just something different. It's a different way of comparing data values, but it still tells you, compared to the rest of your data values from your data set, how important or significant something is and how your data value relates to the rest of the data values. Okay, so if you look at the word percentile, it has the word percent built into it. And remember that with a percent, you've got 0% and 100%, and then all the percents in the middle, in between them. So it makes sense, it should make sense, that there are a total of 100 different percentiles. So P1, P2, all the way up to P99. And they divide your set of data values into 100 groups with about 1% of the values in each group. The only thing that's bugging me about, this is taken out of our book, I only see 99 percentiles here, because they start at 1 and they're going up to P99. But the book says there are 100 groups. I don't know if that's a typo or not. It's not too incredibly important, but you know, there are total, I see only 99 here. The book says there are 100 groups, with about 1% of the values in each group. Okay. Which, just think of them as percentages when you're trying to understand them. So the second percentile, think of that as like 2%. And the P99, the 99th percentile, think of that as like 99%. That should be a rough idea about what a percentile is. And then in more detail, how do you calculate a percentile? Well, if you have a data value, you do have to write all of your data values in increasing order. But then if you want to find the percentile of a particular data value, you can use this formula, which says percentile of a data value x equals the number of values less than x over the total number of values times 100. Okay? So I think an example is probably the most helpful way to understand a percentile. So let's jump into an example. Example, finding a percentile. The table lists the 50 Space Mountain wait times. It's a favorite example in our book. We keep coming back to it. They're arranged in increasing order. Find the percentile for the wait time of 45 minutes. So when you're doing your homework, keep in mind that you do need to write the data values in increasing order. So the smallest data value first, and then the next smallest, and so forth. However, in this example, that's already done, and on some of your homework problems, that's already done. But make sure you look through before you start the problem, and make sure that it's actually in increasing order. But this one is in increasing order, so we don't have to do that. Okay, so how do we find the percentile for the wait time of 45 minutes? All we have to do is look at the formula and correctly identify each part of the formula. So let's go back to the formula. Okay, so the formula is percentile of a data value x equals the number of values less than x over the total number of values times 100. So here, our data value x that we're trying to find the percentile of is given to us as 45 minutes. So this is x. So x equals 45. All right. And then we need the number of values less than x. So the number of data values less than 45. We're going to need that for our numerator. So going back to this table, we need to locate 45, which is right here. By the way, you want to look at the lowest 45. So if there were multiple 45s, you would look at the first one. Okay, so here's 45. Now to use the formula, we need to count how many data values are less than 45. But fortunately, they told us that there are 50 wait times. And if you'll notice, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns, and 1, 2, 3, 4, 5 rows. So that means this is 10, 20, 30, and then here we're at 31, 32, 33, 34, 35, 36. So I'm counting, because they're in increasing order, it's very easy to count. There are 36 data values that are less than 45. Okay? So 36 data values that are less than 45. So using this formula, the percentile of 45 equals, well, we said there were 36 data values less than 45. So percentile of 45 equals number of values less than 45, which is going to be 36, over the total number of values. Remember that we said that for these for this data set, there are a total of 50 wait times. So 50 data values. So the total number of values is going to be 50. So we have 36 over 50, and then we have to multiply times 100. But it should make sense, just looking at the word percentile, that it's a type of percent. It should make sense that you would multiply times 100 to get a percentage, right? Because that's the same thing you do if you have a decimal, you multiply times 100% to turn into a percentage. So that's kind of why you're multiplying by 100. And then the 36 divided by 50 basically is just going to tell us where that data value is in relation to the other data values as a percentile, okay, which is, really a type of percentage, or a lot like a percentage. So then how do we do this on the calculator? You may be able to type it in all at once, or you could do it in 2 steps. So we could do 36 divided by 50, press enter, that gives us 0.72, and then we multiply times 100. Okay, so this is the same as 0.72 times 100, which is 72. Okay, and what that is that we just found is the percentile of this data value 45 for this example. So that means the percentile of the data value 45 is P72. So P stands for percentile, and then the subscript of 72 means that we're in the 72nd percentile. So let's go back to the slides to interpret that a little bit to see what this means. Okay, so as you can see, the book got the same percentile as I just did. Percentile was 72. And then the interpretation of this is that a wait time of 45 minutes is in the 72nd percentile, as I said. This can be interpreted loosely as follows. A wait time of 45 minutes separates the lowest 72% of values from the highest 28% of values. Now, technically, you don't need a lot of that interpretation part for your homework, but it's good to understand what this stuff means and why we're learning it. So how did they get 28%? Well, like I said, a percentile is really just a type of percent or percentage. So if you have 100% total for all of your data values, and we're at P72, that means there are 72%, approximately 72% of the data values are below P72. And then approximately 100% minus 72 is 28% would be above P72. Okay, so again, the way they got 28%, even though you probably won't necessarily have to calculate it for your homework, the way they got 28% was they just did 100% minus 72. Okay, so 100% minus 72 equals 28%. All right, so P72 in this particular example is 45 minutes. And again, it just means that if you have a wait time of 45 minutes, that means out of our data set, 72% of those people who waited at Disney World had a wait time that was less than yours, and about 28% had a wait time that was greater than or equal to yours. But they say loosely because it's not exactly 72% that are below and exactly 28% that are equal to or above. But it's still helpful, right? Because, I mean, what would it mean if you were in the first percentile? That would mean that your wait time was incredibly short. Whereas if you were in the 99th percentile, that would mean you would have some of the longest or either the longest or one of the longest wait times out of all the data values. Okay. And then in our next video, we'll talk more about percentiles. But here we just wanted to do an introduction. And so I will see you in the next video, part 2, where we dive more into percentiles, and then we learn about quartiles, and then also box plots. So thank you for watching. See you next time.